by Aidan Lindberg on Hodge theory of Poisson varieties and non-perturbative quantization. And I should switch the camera to him.
Yeah, I think once I start speaking, it changes. Yeah. Automatically. Okay, great. So first, I'd just like,
Can I check
yeah.
the microphones on?
Yeah, there's a green light.
Okay, thanks. Yeah, so firstly, I'd like to thank the organizers for giving me the opportunity to speak to you today. So what I'm going to talk about is a joint work in progress with Quantization, which was a sort of outgrowth of my master's thesis that I completed under his supervision. So throughout the talk, X will be a smooth, affine variety over the complex numbers. Okay, so story begins with Poisson structures. On X, and Kontsevich in the late 90s proved that these always admit a canonical formal quantization to an associative algebra. So, right, formal associative algebras. Okay, and how this works is the output is some associative product, which at lowest order is the usual commutative product. At first order is given by the Poisson bracket of two functions. And then the higher order terms are given by a sum over graphs, where to each graph we associate some differential operator as well as some weights. Okay. So one of the wonderful things about Kontsevich's solution to this problem is that not only does he prove there is a canonical quantization, he gives us a formula for how to compute this. It's constructed. So let's look at some examples. If we take the simplest Poisson bracket, PQ is equal to 1, well, a simple Poisson bracket, then Kontsevich's quantization, which I'll write O H bar X. This is given by following algebra. We have two generators, and the relation is that their commutator is equal to H bar. So this is the Moyau quantization. Okay. Another example that we've seen a bit of in some previous talks is a sort of log version of this, where P and Q now their Poisson bracket is lambda times PQ, where lambda is some complex number. And in this case, the quantization looks as follows. P star Q is something times PQ, and Q star P is the same thing, the minus sign, times QP, where what is this S of H bar lambda? This is equal to 1 plus lambda H bar over 2 plus lambda H bar squared over 24 minus, I swapped my order, H bar lambda cubed over 48 minus H bar lambda to the 4 over 1440 plus H bar lambda to the 5 over 480. And then at order 6, something interesting happens. H bar lambda to the 6. And here we get 251 over 2048 times zeta 3 squared over pi to the 6. And then there's some other rational terms appearing here. Okay, and then there's other stuff. So what do we see? From an extremely simple Poisson bracket, Kontsevich's formula is producing conjecturally irrational numbers at low order. So this was calculated in a a paper of Banks, Panzer, and Pin in 2020. And they used computer software to calculate this. And the computation involved amassing a database of over 50,000 graphs to get these numbers you're looking at. So what's the takeaway from this? The takeaway is that this is an extremely complicated formula. And if we want to actually understand what the algebras, these quantized algebras are, we need some sort of strategy. So the strategy that I'll tell you about, again, due to Kontsevich, is to complete this morphism. So Poisson structures on X, modulo gauge equivalence. These map formally to associative deformations, well, let's say associative algebras. And what we want to do is complete this to a triangle, where at the bottom we have some Hodge structures. Okay, so the idea is that this is complicated, but maybe from each of these sides we can extract some linear algebraic data. And then if this knows enough about both sides, then perhaps instead of doing this, we can traverse the diagram this way instead. Okay, so that's the strategy. So if we want to prove that a given algebra, which we think of as like a candidate for the quantization, is the quantization of given Poisson structure, we associate some Hodge structures to them via these maps. These are period maps. And if these period maps are locally injective, then we call this a Torelli theorem. And in this case, this says that locally a Poisson structure is determined by its Hodge structure. So this is the strategy. And we'll see it in great detail in an example at the end. So to do this, I need to tell you what a Hodge structure is. So this is a definition, which I'm going to do in parallel with an example, both due to Deligne. So a mixed Hodge structure, which I'll denote MHS. So this is, first of all, an abelian group. So a finitely generated Z module, H Betty. B stands for Betty. And over here, what I want to have is my variety X as before. So this is the example part. I want to take my variety X and I want to compactify it to some proper variety. And I want that the normal crossing, or the boundary, the compactification divisor here, that this is simple normal crossings. Okay. So in this example, the Betty data is just given by the singular cohomology of the associated complex analytic space. The next piece of data we need for a mixed Hodge structure is a C vector space, which I'll denote H de Rham. In this example, this is the de Rham cohomology of X. I need a comparison isomorphism from the complexified Betty to the de Rham. You can think of this as the de Rham isomorphism. Okay. I need a increasing filtration on the rationalization of H Betty. Okay, so this is W for the weight filtration. Call this the weight filtration. Okay, in this case, this is where the normal the compactification comes in. This this weight filtration indexes the strata of the compactification device. Okay, I've run out of vertical space, so let me continue this over here. The last piece of data I need is a decreasing Hodge filtration. Which I'll denote F upper bullet. And this is a filtration by complex vector spaces on the direct data. Okay, so in this example, this is given by, so example, in fact, this is the filtration by forms. So to calculate the cohomology, we can use the complex of log forms on this compactification. So you can think of the Hodge filtration as just being the degree of a form. Okay. So this is a mixed Hodge structure. Given this data associated to a variety, we have a canonical mixed Hodge structure on here. And Deline also proved that this mixed Hodge structure, so which I will denote just H of X, this is independent of your choice of compactification device. Okay. So, sorry, I missed one essential piece. We also need that the associated graded of this weight filtration. So I take the jth graded piece of the weight filtration on the complexified Betty data, that this gives us what's called a pure Hodge structure. So that's just a direct sum decomposition into these subspaces HPQ, where HPQ conjugate is HQP. This is mimicking the cohomology of forms on like a compact Kähler manifold. Okay, so a mixed Hodge structure is like a way of taking a bunch of extensions of pure Hodge structures if you want. Okay, so what I want to do is first give an example of this. So L or ZL, this is a mixed Hodge structure, which is the Elf Tate twist. Okay. So this has Betti data equal to 2 pi I to the L times Z. And this only lives in weight minus 2L. So it's pure of weight minus 2L. Okay, this is a very simple example. This means that the weight filtration has associated graded, which is trivial, except at this 2L piece, minus 2L. And here the H theorem is just C with the obvious comparison isomorphism. So you can really think of this as just a way of keeping track of factors of 2 pi I with appropriate weights. Okay, so if I have a mixed Hodge structure, so then I can tensor with one of these Tate twists to produce another mixed Hodge structure, which is by definition the tensor product of your mixed Hodge structure with this Tate structure. Okay, so in what's coming, there will be L's appearing like this. This just means that I've taken the tensor product with this Tate Hodge structure. Okay, so what I want to do is reinterpret this H mixed Hodge structure in terms of topological K theory. So I need to tell you what the Betti data is. So the Betti data is going to be the topological K theory of the associated analytic space by a theorem of Atiyah and Hirzebruch. This maps isomorphically over the rational numbers to the direct sum of singular cohomology groups. So dot plus 2L. Okay, and we just saw from this example here that each one of these graded pieces has a natural weight filtration on it. So I give this weight filtration so that this turn character is an isomorphism of Q vector spaces. Okay, so all the data on here is just coming from the usual case via this rational turn character. Okay, so that's the Betty data. On the theorem side, we define K dot theorem of X to be similar to this. We're going to take the direct sum over theorem cohomology groups now. Again, twisted by L. Okay. And here, the Hodge filtration is by the degree of forms. Okay. So this is what I have. Are there any questions at this point about this? Okay. Yeah. Yeah, exactly. There's a way to do it all naturally.
Can you repeat the question? So for the people in Zoom, sorry.
I was just clarifying when he took the tensor product of the mixed Hodge structure with ZL, what he meant, and he said.
Okay, so at this point, up to this point, there have been no Poisson structures. I'm now going to choose a Poisson structure. Remember, I had this compactification. Now I want to choose this compactification so that I want to turn on a Poisson structure here. So I need that this boundary divisor is smooth normal crossings and simple normal crossings and Poisson. Okay, this means that we have a bivector in this sheaf. So it's made of pieces which are tangent to this divisor. And the example to keep in mind here is where X is C star to the N and X bar is Pn. Then our Poisson structure is determined by a number of parameters, lambda ij. Okay, so this is like what we saw at the beginning, except that now this is on an arbitrarily large torus. Okay, so this is the example you should keep in mind. And the theorem, one of our theorems is that the data, I'm sorry, I haven't told you. Yeah, so theorem, the data of X with compactification and this Poisson structure defines a mixed Hodge structure, which we denote K dot X sigma, whose Betty data is the exact same as before. Nothing has changed. This has theorem data. Again, the exact same as before. Nothing has changed. The only things that change, sorry, this should be a W, is that we're going to deform the Hodge filtration by exponentiating the operator, which is contraction with the bivector. So remember, this is a filtration by degree of forms, and now I'm going to deform this filtration by this operation. So this was the Chern character, but now I'm also going to twist this by the A hat class of the map. Okay. This is just some characteristic class. So the theorem is that this actually defines a mixed Hodge structure. And the proof basically boils down to the same degeneration argument as in the classical case. One thing to note here is that we do not know that this mixed Hodge structure is independent of the compactification that we choose. So the way you get around this in the case where there is no Poisson structure is you can appeal to resolution of singularities, but we don't have a theorem like that in the Poisson case. We don't know that we can, yeah, so that's something we're thinking about. And to the quantized algebra, which I'll denote like this. This is what's output by Kontsevich's formula. We also associate a mixed Hodge structure, which I'll denote K dot OX H bar sigma. Okay, so what is the RAM data? We'll play this first. This is given by the periodic cyclic homology of this algebra. This is an invariant, which you can define for any associative algebra, which is a replacement for theorem cohomology if you want. The Betti data, I don't really have the time to explain in great detail, but this is if this is like the parameter space of non-commutative algebras, then we have this central fiber here, and at the central fiber, all of the non-commutative invariants agree with the commutative invariants. So this is really taking place in some formal neighborhood. And what we do is we parallel transport this k Betti of x, which is defined as before, we parallel transport this to this other fiber, this non-commutative fiber using the Gauss-Gauss-Mann connection. Okay, so I don't have time to really explain this in a lot of detail, but if you want, we can talk about it afterwards or later. Okay. So then the main theorem is that formality induces an isomorphism of these Hodge structures. So K dot. Okay. Where this I'll just call formality. So what this means is Kontsevich's theorem quantizes the Poisson structure, but there's been a lot of work over the past 20 or so years by people who have found ways to quantize other parts of the algebra. So important names here would be Willwalker, Cattaneo, Felder, Rogers, Dolgeshelt, Markin, Segan, Getzler, a lot of people. And others, which I did not mention. Okay, so how can we use this? Well, let's think about the diagram at the beginning. We have a Poisson structure. We associate a mixed Hodge structure. We have some non-commutative algebra. We want to associate a mixed Hodge structure. And the idea was to compare these if we had some Torelli theorem. So the theorem is that if x and x bar is log Calabi-Yau, then Torelli holds. Okay. So let's do an example of this where this is true. So let's take x again to be a torus and the Poisson bracket to be determined by these parameters lambda ij. Okay. And let's take our candidate non-commutative algebras to be OQ, which this is the algebra with generators x1 and xn along with their inverses, subject to the relation that xi, xj is qij, xj, xi. We're really here this qij is an invertible formal power series. Okay, so from Kontsevich's theorem, you can determine that the quantized algebra actually has to have this form. So all that we need to figure out is what are these parameters qij. If we can know what those are, then we know the quantized algebra. So draw this. We have lambda ij's. This is Poisson. We have our OX, or yeah, OXQs. This is the non-commutative side. And we need to calculate what the period maps are. Where this map is Kontsevich's forms. Okay, so I'll show you how to calculate this period map on the Poisson side. We know that the topological K theory splits as the direct sum, in this case of H2L X. This is actually defined integrally here. So this looks like Z in degree 0. In degree 2, we have the second exterior power of Z to the N, twisted by -1. And then there are higher ordered units. Okay. Now remember, this comes along with a weight filtration. And the second piece of the weight filtration on this from this, we see that this gives us an extension in the category of mixed Hodge structures from this mixed Hodge structure to Z. Right, the weight filtration is a filtration, so we get this, and it's a classical computation in Hodge theory that this is actually isomorphic to C star to the N choose 2. So when you take a Poisson structure of this form and you plug it into here, you calculate what is this extension class. The number that's produced right here is the exponential of H bar lambda ij, or really it's just lambda ij, but if we want to plug this into Kontsevich's formula, we need to put an H bar on here. Okay, now if we do the exact same computation with this non-commutative algebra, we get exactly Qij. So because this induces an isomorphism of Hodge structures, these numbers actually have to agree. And in this way, we've calculated the quantized algebra precisely and not perturbatively. Thanks for your attention.
Any questions? Yeah, that's right.
So I just wanted, you mentioned the connection on periodic cyclic homology.
Yeah.
And when I wrote the original paper, I didn't notice that I was writing down Griffith's transversality. So I'm just really curious if you rely in any way on Griffith's transversality.
So we need that. But when we work formally, there's no issues about monodromy. So we don't actually have to worry about whether this preserves the weight filtration.
Mm.
So that's not really an issue. If we wanted to do this non-perturbatively, then we'd have to think about this. And in the what we'd like non-perturbatively is that there's this invariant called topological K theory of non-commutative spaces, which was developed by Anthony Blanc and Walker and Friedman, I believe. And this should be the Betty lattice, and it should be parallel or covariant constant with respect to your connection. That's the idea.
Another question? I'm actually curious, like what you said, like at the very beginning, you have all these numbers, like also these theta coming out, but in the end, you present over there is just exponential, so it's just factorial, n factorial. What are they related?
Oh, so do you mean this like S of H bar lambda
Yeah.
number? So really, Kontsevich gives you an isomorphism. He gives you a particular representative of an isomorphism class of this algebra. So this has to be gauge equivalent, or this is isomorphic to what Kontsevich is. Yeah, to this one from the beginning. Yeah.
That one can be simplified.
Yeah, exactly.
Nice. Okay, so if no more question, we restart at 3 o'clock in 2 minutes.
Yeah, it's